On to Chapter 8. So in Chapter 8, we will be talking about delocalized electrons. So this is going to be sharing of electrons between more than one atom. So our first part of the chapter, we will be discussing predominantly a type of sharing that's called resonance. Right, we've mentioned this before, you've probably seen it before in Gen Chem. And then we will talk about different scenarios where resonance can influence reactions. All right, so we will look at some of the reactions we've looked at up to now and see what happens if we have reactants that can have resonance either as their reactants or as intermediates in the process. And so this will just kind of expand the type of reactions we can look at. All right, so let's start out by looking at an example of resonance that we have talked about already. All right, so in Chapter 1, part of the chapter was on acid-base chemistry, right? And in that chapter, we compared two acids. One at the bottom is acetic acid. And we compared the acidity of acetic acid to that of ethanol. All right, so we've got a carboxylic acid versus an alcohol. And so if we consider their acid-base chemistry, we know that an acid will donate a proton to give its conjugate base, plus here's the proton. Okay, and we can do that for acetic acid as well. And we talked about how acidity is related to the stability of the conjugate base. All right, so for each of these molecules, so here's the conjugate base from ethanol, and here's the conjugate base from acetic acid. Okay, so we would ask the question of which is more stable, okay? Because the acid that has a more stable conjugate base is going to be a stronger acid, all right? So we can turn this around and think about it in the opposite sense as well, is we can get a representation of the acid strength if we look at the pKa's. So the pKa for acetic acid is about 4.8, and the pKa for ethanol is around 16. All right, so which one of these is a stronger acid? Acetic acid or ethanol? All right, so of course we know this is going to be the stronger acid because it has a lower pKa. Okay, if it's a stronger acid, it must mean that it has a more stable conjugate base. All right. The added stability comes from the delocalization of electrons. All right, so in this case, at the bottom, where we have non-bonding electrons on this oxygen, on an atom, an oxygen, next to a pi bond, this is a situation where we can have resonance. So what happens is a non-bonding pair of electrons moves down to form a pi bond, but because this carbon can't hold any more electrons, right, it already has 2, 4, 6, 8 electrons around it, it has to give up a pair of electrons. But it can give up its pair of electrons to the oxygen. Right? This oxygen up here already had 2 pairs, and so we can come up with a new structure that looks like this. Now there's a single bond going up to this oxygen. Right? We know that oxygen with 3 non-bonding pairs and a single bond has a minus charge, and it forms another oxygen with a pi bond. All right, so these two structures are what we call resonance contributors. Because they both contribute to the overall structure of the molecule. So one thing that we'll talk about several times in this process is that neither of these resonance contributors shows the true structure, but in fact the true structure is a hybrid of the resonance contributors. All right, so we'll see more examples of that. To show that these are resonance contributors, we will, usually this will be straight, but we'll use a double-ended arrow like this. Okay, so this kind of arrow is reserved for resonance, and that could be compared to the other kind of arrow up there like this. This is for equilibrium. So we all have to always remind ourselves when we have resonance contributors, it's not that we have two structures going back and forth like in equilibrium. We have one structure, and these resonance contributors show different contributors to that one structure. Okay, so I'll show you more about this as we go on. So let's look at a few rules that we have for drawing resonance contributors. Okay, so this is what I said just a minute ago. So individual resonance contributors have nothing to do with reality. Okay, so they're not the true structures. The true structure is a weighted hybrid of all the different contributors. Okay, when we have resonance contributors, only electrons, which can be either pi or non-bonding electrons, move. Okay, the atoms can't move. Can't break, well, we can only move electrons so we can make single bonds to double bonds and things like that. Okay, the total number of electrons in all resonance contributors have to be the same. sp3 hybridized atoms cannot accept electrons, all right, because it already has an octet of electrons. And the last thing is we can never break sigma bonds when we have resonance contributors. We just break pi bonds to make single bonds. All right, so let's look at a few scenarios when we have resonance. Okay, the first situation is where we have a non-bonding pair of electrons on an atom next to a pi bond. Okay, so I'm just going to do these kind of in a generic sense. We're going to have X, Y, and Z. So we have three atoms connected to one another. They could be carbons, they could be oxygens, they could be nitrogens, things like that. Okay, so in this first one, we're going to have a double bond here, and we're going to have a pair of electrons on the X atom. Okay, so we have non-bonding pair of electrons on an atom next to a pi bond. In this situation, the electrons can move toward the pi bond. That Y atom would typically have a complete octet already, and these electrons would move to Z. Right? So we use our resonance arrows, and we would have a resonance contributor that looks like this. Okay, sometimes these atoms will have charges on them. It just depends upon what atom we have. Okay, so this is one common scenario. In fact, this is the scenario that we had for the carboxylic acid. All right, because in that case, right, we had O minus. Let's put an R group here. We had O minus, so here we had non-bonding electrons next to an atom carbon with a pi bond, right? So in this case, we pushed our arrows like this and like this. Okay, so that falls into this top situation. Okay, the second generic type of situation is we have an atom with a cation on it next to a pi bond. Okay, so in this case we're going to have a plus charge here. In this case, the pi electrons are going to move towards the plus. So this will go over this way, and this will give us a resonance contributor that looks like this. Now, the double bond will be to X, we'll have Y, and the cation will be now on Z. Z is now short of electrons. Okay, the third generic type of resonance situation we won't see much until the very end of this semester. In this case, we have a radical. So a radical is a lone electron, an unpaired electron on an atom next to a pi bond. Okay? So in this case, we draw it a little bit differently. When we draw single electrons, we draw single-sided arrows. So we're going to move that electron, and we're going to combine it with one of the electrons in this pi bond. Okay, we're only going to take one of those. So we're going to form a new pi bond. We're going to split this pi bond, and the other electron is going to go over to Z. So we've shifted the pi bond to the other side, and now Z holds the radical. Okay, so we'll see, especially these top two scenarios, a lot. And then later on the last chapter of this semester, we'll look at radical reactions, and we'll see this example at the bottom. All right, so let's put some real atoms into these situations. Okay, so let's look at the first one. All right, so which scenario does this fit into? 1, 2, or 3? All right, so we have a cation on an atom next to a pi bond. So this is scenario 2. So what do we do to show the delocalization of electrons? Okay, so in this case, the pi bond moves toward the plus. Okay, so we have our resonance. And so now we have a pi bond here and a plus over here. Okay, this is called an allylic cation. Okay, remember the allylic position is the position adjacent to the double bond. All right, so these are both resonance contributors, so if we wanted to draw out what the true structure might look like, put this in quotes here. Okay, so the true structure would have the same carbon skeleton, but notice that in our two contributors, in one case the double bond's here, and in one case it's a single bond there, and in this case it's double bond there, single bond over here. So in the true structure, we're going to have partial bonds here. All right, so we have two partial bonds, and then we're going to have a partial plus at this end and a partial plus at this end. So this shows that the electrons are shared between these two partial bonds and sharing the plus charge over those two atoms. Okay? All right, so the next one includes this functional group here. This is called a nitro group. Okay, nitro groups are kind of interesting because they have, they're net neutral, but they have a plus and a minus. All right. So one thing, in order to be able to do resonance, we need to know where the non-bonding electrons are. So we know that if oxygen has a minus charge on it and one bond to it, it's going to have 3 pairs of non-bonding electrons. If it has a double bond to it, it's going to have 2 pairs. Okay, so what scenario does this one lie in? All right, well, this one has a pair of electrons on an atom next to a pi bond. Right, so this is scenario 1. And in that case, the electrons, the non-bonding electrons, go down to form a new pi bond, and these electrons go up onto the oxygen. So our resonance contributor would look like this. Still have a plus on the nitrogen. Right? So we have this resonance contributor. So this is similar to the carboxylic acid case, right? Because if we made this atom in the middle a carbon instead of a nitrogen, then this would look like that carboxylate anion. All right, so the true structure again would be a hybrid of these. Right, so we're going to have a partial double bond here. We're going to have a partial double bond over here. We have a plus on the nitrogen and a delta minus on this oxygen and a delta minus on this oxygen. In fact, we'd have a minus 1/2 charge on one oxygen and a minus 1/2 charge on the other oxygen. Okay, so let's look at one more. All right, so here we have 3 pairs of non-bonding electrons on this oxygen. Let's neaten that up a little. And so just like the case above, we can donate these electrons, and then the pi electrons are going to go to the next carbon, the next atom, which is a carbon. Okay, so we end up with a double bond up here, and a pair of electrons over here, so it puts a minus charge on the oxygen. Okay, so in this case, it's still the same scenario as the one just above it. And so our true structure would look something like this. Right, a partial bond here and a partial bond here. So which of those two atoms do you think would hold more charge? Do you think the oxygen would hold more negative, or do you think the carbon would? All right, so what I would say is that this oxygen, let's say minus minus and delta minus down here, so a little bit more of the charge would be held on the oxygen because it's more electronegative and it's better at holding that kind of charge. All right, so that's some examples of resonance that fall into the top 2 generic scenarios that we talked about. So let's look a little bit more at these different resonance contributors and see if we can talk about which ones are more stable. So the structure is not always going to be an equal, not each resonance contributor is going to contribute equally to the true structure. Okay, it's a weighted hybrid in that the more stable contributors, resonance contributors, will contribute more to the true structure. Okay, we can draw some resonance contributors that follow all the rules, but they can be very unstable, and so they're not going to contribute much to the character of the true structure. Okay, so here's some rules about stabilities of resonance contributors. Okay, and these are kind of in order of priority. So in the most stable or more stable contributors, all the non-hydrogen atoms will have filled shells. Okay, we'll have 8 electrons around them, or octets of electrons. Okay. In more stable contributors, negative charges tend to be held by more electronegative atoms, while positive charges will be held by more positive atoms. Okay, so like the last example we saw, when the minus charge is on the oxygen, is going to be a little more stable than the minus charge on the carbon. All right, more stable contributors minimize the separation of charges. And so if we're just making resonance structures that add a lot more charges, then those are going to be less stable. All right. Another point is the greater number of relatively stable contributors, the greater the stability. Okay, the more resonance structures or more resonance contributors that a molecule has, the more stable the true structure will be, and the more nearly equivalent resonance contributors, the greater the stability. So, for example, that carboxylate anion for acetic acid, it has two equivalent resonance contributors where oxygen is holding the minus charge in each case. So that makes it quite stable. All right, so the increasing stability resulting from resonance is called the resonance energy. Okay? All right, so let's look at some more examples. For each one, we'll want to decide which of the generic resonance situations that we're in, and that will allow us to decide how to do our resonance. So let's look at the first one. All right, we have this CH2 group with a plus, which is next to this is a benzene ring. Okay, so what do we have? Okay, so in this case, this really would be that second scenario, right? We have a carbon with a cation on it. So we have a cation adjacent to a pi bond. So we have this part here, and so in these cases, the plus charge, or the pi bond moves towards the plus bond, the plus charge. Okay, so let's do that and draw our product. All right, so we now have a double bond going to the CH2 group, and our plus is here. All right, so an interesting thing about this structure is that now we also have another plus next to a pi bond. So we can do the same type of resonance again. We can move, we can move this pi bond towards the plus. We get another resonance form, another resonance contributor. It puts the plus over on this position. We can then even do this again. We can bump it over one more time. And so then we have a double bond here, a double bond here, and a plus there. In fact, we can even do this one more time. We can take this double bond that sticks off of the ring, move those pi electrons down, and we get the plus back out on the CH2 group like this. All right, so is this the same as what we started out with? All right, if we compare this structure with this one up here, are these just the same? Well, no, they're not exactly the same, because notice that all of the double bonds are in opposite positions to where they are up here. So in fact, we can push these electrons around in a ring like this, and if we do that, we get back to our starting point. All right, so if we were going to draw out the true structure for this, we would notice that the plus is held by this carbon here, it's held by this one, it's held by this one, and we're back to the outside. So if we were going to draw the true structure of this one, we would essentially have partial double bonds all the way around here, and a partial double bond out here, and there, where would we see the charge? Right, so then we'd have a delta plus here, a delta plus here, delta plus here, and a delta plus over here. Right, so we see that the electrons are spread all the way around this system, allowing the distribution of this plus charge. That gives a lot of resonance energy. It allows this molecule to become much more stable. All right, so let's look at the next one. So this next one doesn't have any charge on it, so how do we know what type of resonance we could have? Right? So what we do have is we have some bonds that are polar. Right? So for example, if we look at this carbon-oxygen double bond, we know that oxygen is more electronegative than carbon, so that oxygen would have a delta minus on it, leaving a delta plus on the carbon. All right, we can reinforce this with resonance. If we move these pi bonds up onto the oxygen, we can get a resonance structure that now looks like this, with a plus here. And then notice what we have now. We have a plus on this atom next to the pi bond. So that's the same situation we had up here. So we can move this pi bond down like this, and it gives us this resonance contributor. The plus here and a minus over here. Alright, so we could do this in the opposite way as well. Alright, so let's think about what if we started out in the beginning, instead of moving the electrons up on the oxygen, we move these electrons down on this carbon. Then what would it give us? Right, so then, right, this oxygen already had 2 pairs of electrons, so it would still have those 2 pair. Have a single bond here, and another pair here. And how would our charges be? Right, we'd have a minus charge on the carbon and a plus charge on the oxygen. Right, so how do you think the stability of this structure is relative to the stability of this one right over here? Okay, so let's compare these. Alright, so which one's more stable? Right, so I would say that this one is more stable than this one, right? Why is that? The reason is because this structure puts the most, or the negative charge on the more electronegative atom, right? Minus charge on oxygen, which is more electronegative, plus charge on carbon. This one has it just opposite, plus charge on the electronegative atom, minus on the more electropositive atom. So this one would be much less stable. Right? So in fact, it probably wouldn't contribute much to the overall structure or character of this molecule. Mostly what we would see is that there's a delta minus on this oxygen. There is a delta plus, where we already wrote this, and another delta plus over here. Okay? We could in fact write it with, there'd be a delta minus here as well. Okay, so we have alternating minus plus minus plus. Alright, so let's look at the last one in this slide. So what type of scenario do we have in this slide? Alright, so we have this atom here with non-bonding electrons, and it's next to some pi bonds. So the way that we did our resonance then is we donated the electrons to form a pi bond. The next atom had to give up a pi bond. Right, so that would get us to a double bond here. Nitrogen always has a plus charge when it has 4 bonds to it, so it keeps its plus charge. There's the new non-bonding electrons, and here's another pair here. Okay, so if we went and did our formal charge calculation, we'd now find that there's a minus charge on this nitrogen. Okay, so do we have any other possibilities here? All right, so we have some other possible resonance. We could move, let's just move this pair onto this nitrogen. That would give us nitrogen. Here's the pair I just put on there. Now we have a single bond, nitrogen, and this nitrogen just has two non-bonding pairs on it. Okay, so what would be our charges here? Alright, so this one is actually neutral. There's no charge on it. All of the atoms are neutral. How about if we did the same thing here? We moved these electrons over to here. Let's draw one more. H2C, single bond to nitrogen. There's the pair that came from that one. And now I have a double bond over here. Two non-bonding pairs. We still have a minus here. And where's the plus going to go? The plus would be back over here. Alright, so let's look at these different resonance contributors. Alright, and try to decide which one would be the most stable. Alright? Okay, so what do we look at first? All right, so the first thing we're going to look at is whether or not all of the atoms have complete octets. Alright? So what about the first one? Okay, this one here. Alright, he has two here, two there, and two for each of these carbon-hydrogen bonds. So this one has an octet. What about the nitrogen? Yep, there's 4 bonds, octet. Here, 3 bonds and a non-bonding pair. These have complete octets. Alright, what about the next one over here? Okay, this one has 4 electrons here, 4 over here. That's a complete octet. This has 4 bonds, 4 octet, 2 bonds, 2 non-bondings. This has a complete octet. Alright, what about the one on the right? Okay, so the atom here, it's just like over here, so that has an octet. This nitrogen, 2, 4, 6, 8, has a complete octet. What about this nitrogen? No, this only has 2, 4, 6. This has no octet. Okay, that's going to make this one less stable. Alright, what about this bottom one down here? Okay, the bottom one has octets on both nitrogens, but this carbon only has 3 bonds on it. No octet. Alright, so the two that have no octets are going to be less stable than the two that have complete octets. So let's compare these two, this one and this one. Can we compare these in stability? Alright, in this case we have a minus on a carbon, plus on a nitrogen. Over here we have a plus on a nitrogen, which is the same. We have the minus on the nitrogen. Which one do you think is going to be more stable? Right, so I would probably say that this one should be the most stable. Why is that? Because the minus charge is on nitrogen rather than carbon, and nitrogen is more electronegative. Alright, so we can pick out some relative. Okay, it looks like on this slide we've already done 2 of these. We've done this already, so that was a waste. So let's look at the next one. Alright, so this is a type of a functional group called an amide. And it's the same type of functional group that connects amino acids together. So for example, amino acids have structures like this. Here's an OH, here's the acid part, and here's the amino part. And usually they have some group here, what's called the side chain. Okay, we can draw another one over here. Has the same structure, except for what it has on the side chain. Okay, I'll make this with a prime on it. That means that that one could be different than the other one. Okay, so these two can react with one another, and if we lose one H from over here and an OH from this side, we lose a water molecule, and then we link those together. Rn, we have this H, and then we have this R prime and NH2. Okay, so this bond here is an amide. Alright, and these are amino acids, and they're linking them together, so proteins are made up of lots of these amino acids. So let's look at an interesting property of amide bonds. Alright, so nitrogen, when it has 3 bonds, it has a non-bonding pair of electrons. Usually in this case, we'd say, oh, there's 3 single bonds and a non-bonding pair. It should be sp3 hybridized, and it should be tetrahedral. But this has an atom with a non-bonding pair next to a pi bond. That's one of our generic situations for resonance. And so we have a resonance form, resonance contributor, that looks like this. All right, so in proteins, it's this resonance contributor is actually significant, and this whole thing is planar. All right, so this resonance plays a big role in the structure of these amides, and so, in fact, this whole part right here would be planar. Okay, so resonance influences the shape of this molecule. So instead of being tetrahedral at that nitrogen, it's planar. Pretty cool, huh? All right, so one more example here. Let's look at some different types of pi bonds. All right, so the top one, notice that we have 2 carbon-carbon double bonds, and we have a carbon in between. And what's the hybridization of that carbon in between? Right, so that's an sp3 hybridized carbon. Can it have resonance? No, in order to have resonance, it has to be able to have a p orbital on it. All right, so this we would call an isolated diene. Okay, and so this has no resonance that shares electrons between those 2 pi bonds. Okay? When we have 2 pi bonds next to each other, however, they can have some resonance. So for example, we could move these electrons over here. Right? This whole thing is symmetrical, so we could do it either way. If we did that, we'd be left with a plus here. We shifted our double bond there, and we have a minus over here. Okay? So even though between these 2 structures, this one is definitely more stable, this one over here suggests partial double bond character for this carbon that looks like it's between the 2 double bonds. All right, so it's not a full double bond, but what it does is it causes a restriction in the rotation around that bond, right? We've talked about different conformations, but a diene like this can have 2 different conformations, right? This is equilibrium now, that look like this, right? So all I've done is I've rotated around this bond between them, okay? And so this is very slow. It doesn't really happen as easily as my arrows would show. And so we have two different forms. This one is usually called an S-trans, and this is called an S-cis. And this will play a role in a reaction that we talk about at the end of this chapter. All right. So this last one I think we looked at before. Basically, it's just like the diene up above, right? We've already done this one. Right? We saw that we could have delta minus here, delta plus here, delta minus, delta plus. All right. So right? We've talked about resonance contributors. We've used arrows to convert one resonance contributor to another. Remember, we can only move either non-bonding or pi electrons when we're doing resonance. Okay? We've learned about the relative stabilities, and we've learned how we can decide which resonance contributors are more stable than others, and so therefore which ones are going to actually contribute to the true structure the most. Alright, so in the next video we're going to talk about a very special group of molecules that have resonance. We saw a little taste of this already. This molecule here is called benzene, and it's one of many compounds that are called aromatic compounds, and so they have kind of some special properties.